Hey, Dr. Marble. So this is a project for Jose Garcia, Candice Cardenas, and Kamrynn Schiller with the 2.7 Vpython over motion projectile with and without air resistance.
Okay, so on the first line here, we put this on Vpython program because it prevents integer division with truncation. The second line we also added because it tells the program to use 3D models. On this section here, it's just the input command, which will gather input information from the user, and we have the mass, initial velocity, theta, which is the angle, the radius, and then the viscosity of the fluid. On this section, we have the create launchpad and the sphere. So here we create the ground. In this case, we did a box. And then sphere 1 and sphere 2, the positions, the radius, and then the colors for each individual sphere. On this section, we have the initial conditions. We have time equals 0. The change in time is 0.001. Then we have gravity as negative 9.8. And then we have here the force of gravity, which is the vector in vector notation, 0, g times z of t, 0. On the next section,
we have the velocity of sphere 1, and that's computed by v naught times cosine theta, which is multiplied by the conversion factor pi over 180, and that's for x. And for y, it's v naught times cosine theta, which is also, v naught times sine theta, which is also multiplied by the conversion factor pi over 180. And the k value is 0 because this is in 2D, not 3D. And the same applies for the velocity of sphere 2 and the initial velocity. For the drag force, we have the same x and y and k values, but we multiply it by Stokes' law to get the initial drag. For final velocity, it equals the initial velocity plus the drag force over mass times dt, which equals the final velocity. So the rate is basically just the rate of the calculations being computed whenever the program is ran by the user. And then sphere 1 velocity is equal to the sphere 1 velocity plus the force of gravity. And sphere 1 position is equal to, it controls movement along path, recalculating every 0.0001 seconds. And if sphere 1 y is less than 0, the print command will pronounce specific range and then break, which stops the loop. T plus equals dt, which is
it keeps the time variable for calculations of the sphere. And then t equals 0, we'll set the time back to 0 to start the new calculations for sphere number 2. And so then on the next section, we hold this true for sphere number 2, And on sphere number 2, we have again the rate, which is the rate of calculations being computed. And then on this part, it's the velocity for sphere number 2 is going to be equal the velocity of sphere 2 plus the drag force. For the final velocity, we have it equal to the initial velocity plus the force of gravity times change of time over mass plus the
Drag force.
which is what V of F is equal to. For V initial, again, we have it is equal to V final, and this is just the initial velocity equals the final velocity, because we want the start and the end positions to be at the same spot, which in this case would be 0. And then F of D is equal to, this is the
Drag force.
drag force, which is equal to the force of gravity times Stokes' law times the change in time, which is pretty much the force of air drag times our gravity times dt. And then here we have, if the sphere 2, if the x is greater than or equal to 0, this prevents the velocity from becoming negative or from going under the x-axis. On this part here, we have sphere 2, the velocity of sphere 2 is equal to the velocity of sphere 2 plus the force of gravity plus the force of drag, and this is just the addition of components for the velocity of sphere 2. Okay, so here we have the velocity of sphere 2 is going to be equal to the velocity of sphere 2 plus the force of gravity plus this vector here. Pretty much what this is going to do is it's going to eliminate the drag force after x equals 0. Here on this part we have the position of sphere 2 is plus or equal to the velocity of sphere 2 times the d of t, and this is just going to control the movement every 0.001 seconds, which is our delta t. And then here on this section, if the y on sphere 2 is less than or equal to 0, then this is going to cause the loop to stop when y equals 0. And then here we go back to the print section, and this is just going to print out the range of the distance, and then the break function will stop the loop. And then here we have the mid and the ground, and basically what this is just the mid will be the midpoint between the initial position and the final position, and then the ground would just be what makes the ground fit the distance of the projectile as it runs the program. Okay, so now we're going to run the whole program so you can see how it works. So now we're going to input the mass, which is going to be in kilograms. We're going to use 5. For the initial velocity of the sphere, we're going to use 20 meters per second. For the launch angle, we're going to use 85 degrees. For the radius of the sphere, we're going to use 1. And for the viscosity of the fluid, we'll use 56. And as you see there, the green ball fill first because that is a ball with no air resistance. And then the red one has a shorter displacement from the starting point to the end point because of that air resistance that we added in the program. So that gives you kind of that change in the displacement, and the height also gets affected. And that's pretty much how it works.